the population linear model. So now again, we're talking about inference. So in the population, should we have all the observations in the population? There is a linear model that describes that relationship between whatever those two quantitative variables are. So in the population, the linear model takes on this form where y is the response is equal to beta naught, which is the intercept, plus beta 1, which is the slope, x, which is the explanatory variable, and then some error term that is what we call the residuals. That's the difference between the model and the actual values. But we assume that the errors are normally distributed with a mean of 0 and some variance. So I think sometimes you can also say that that could be 1, but that's just, again, you just divide by sigma squared, and then or sigma, then you get that to be standard normal. So you could always go back and forth. So someone in first block asked, what's the difference between the population linear model and the population regression model? So the regression model is without the error term right there. So it's just, and again, I didn't type this out correctly. This expected value should actually be the expected value of y given x. So in this case, it is actually the conditional expectation. All right, so there is such a thing. All right, there's also conditional independence and stuff like that. There's a lot of other variations of things we learned in this class that are conditional. So in this case, this is a conditional expectation of y given x. So that's basically saying, what do we expect y to be if we know what x is? So in that case, if I plug in a value of x into my linear function, then what should I expect the y value to be as a result of that? So this is the linear model or regression model that we are after. This is the population. So in this case, beta naught and beta 1, the y-intercept and the slope of that line are what we're trying to do inferences on. So in this case, the parameters are the coefficients of that linear model. So right here, beta naughts and beta 1, this is going to be the slope. Beta naughts is the intercept. All right, and these are just the coefficients. So in this case, these are the coefficients of the population model, and these are our parameters that we're trying to either estimate or make claims and test on. All right, so those are the values that define the linear model that describes the population. So if we know what those values are, then we could define that linear model that's supposed to explain the relationship between all or of all of the individuals in the population. But as we all know, that's the population model, so we usually work with the sample, where we get the sample model, which looks like this, where it's just yi is equal to a plus b times x sub I. So b and a are the estimates of the slope and the y-intercept. So these values right there, and your calculator, again, uses a and b, so this is consistent with your calculator. This is the intercept, the estimate of the intercept, and this is the estimate of the slope. So again, our goal is to figure out what does that population model look like, and if I could find, do an inference on the slope and the intercept, then I can get closer to knowing what that model in the population looks like. So that's the idea there. And then this little picture off to the right, we'll talk a little bit more about this, but not go too much in detail. But if the population model, again, it's linear, so it has this form right here. This is the beta naught plus beta 1 times x. That's our linear line. And then you're going to see that at every value of x on the line, the data points, the scatter plot should be symmetrically distributed around that line. So we typically describe that symmetrical distribution of points around that line by a normal distribution. All right, so it'll be a little bit more complicated. Oh, that's why this is here. Sorry, I did include it inside. That's why this is here, right here. This is here, right here. Is because if I want to find the expectation of y given my value of x as a function of x, then at any value of y, I want to say that it's going to be normally distributed. Okay, so again, if I have my scatter plot around this line right here, I want to say that at any value of x, the data points are normally distributed around that line. Okay, ideally, at least. Okay, so that's the model that we're after. One condition that we're going to have to check is linearity. So how do we check linearity? You can look at the scatter plot of the data. As you see right here in the left panel, we see that clearly this is a very strong linear association. And when you look at the residual plot, you see that in the residual plot there's random scatter right there. The thing that we don't want to see is patterns in the data set. So clearly we see a curve there, and that curve is more pronounced in the residual plot. This is why residual plots are important to look at, because the residual plots can tell us a little bit more about the shape than just looking at the original scatter plot. And then notice that this scatter plot, notice that the association is weaker. So in that case, with the weaker association, the residuals are a lot bigger. So there's more spread in the residuals, let's say over here, than over here. So the closer they are to that middle line, would that suggest that the residuals are small and it's a better fit. Okay. All right, so that's one condition that we're going to have to check with these problems. Another condition that we're going to have to check is normality, but it's going to be normality in, you could also check normality in different ways. So one such way that you can check it is looking at a graphical representation of the residuals, because the residuals tell us information about the shape. So if we want to say that the data points are normally distributed around the line, we could just look at the residuals and see if there's a symmetrical pattern in the residuals to tell us more about the original data set. However, of course, if we have a sufficiently large sample size that's greater than 30, then normality is typically okay based on the law of large numbers in that situation. All right, so looking at this again, we basically have a residual plot here. Looking at the residual plot, because we don't see any pronounced patterns, notice that they're just randomly scattered around the line. We would like to say that they are symmetrically distributed around this line, so that again they're obviously centered at that line, but then of course it's not like all the data points are skewed in one side over the other. So in this case, when the line goes straight through the data set, we would hope that it's normally distributed, meaning that the line going straight through the data set, it's symmetrical, the points that are distributed around that line. Okay. All right, another condition that we're going to have to check, so obviously the conditions are very different from what we've seen before. Hold on. Is you on? Mm-hmm. I am. Is it Kamal? As long as he's not doing anything important, I don't mind having him. Okay? Okay, sounds good. Thank you, Ruby. All right, bye. All right, so in this case, another condition that we have to check is equal variance. Variance, again, as you guys know, is the measure of variability. So we want to make sure that as we look at the residual plot, that there's somewhat, again, it's not going to be perfectly equal, but we want to see that as we go left to right, that there's somewhat of an equal spread of the data points around this line. So just to give you guys like a rough idea of what we want to look at, we can just see I got any points of this scatter or the residual plot around the line. We would like to see that that the variance, the variability of the points around this center line is roughly the same. All right. So again, it doesn't have to be perfectly equal because nothing really is, but as long as it's roughly equal, I think we're in good shape, all right? And this is something that we look at the residuals for, so again, looking at the residual plot is very important to check these conditions. In practice, they call it residual diagnostics, all right? Because in order to check the conditions, a lot of the weights of those conditions lies in the residuals. All right. Another thing that does pop up in these type of problems is reading computer outputs. So as a refresher, okay, when you're giving computer output that, again, many of you guys were misinterpreting on that test, all right, the variable that you see right here is the explanatory variable. That's our x variable. And then if you look in the next column, it says coefficient. So what is the coefficient of the explanatory variable in the model? That's going to be the slope, right? So it's, as you guys remember, it's y is equal mx plus b. So what's in front of the x? It's the slope. So the coefficient of the explanatory variable is the slope. The coefficient of the constant, that's just the constant itself. That's the y-intercept. And then it gives you all this other information such as standard deviation of residuals, which could be helpful. R squared, you take the square root of it, you get the correlation coefficients. And then for our purposes today, we are going to now look at this row right here that I'm highlighting in yellow, because if we're going to do an inference on the slope, we're not going to do an inference on the intercepts. So notice that the other columns of this table, such as standard error, that's something we need when we, let's say, construct a confidence interval. T, oh, that T stands for t-test, because we're going to be doing t-test now that we know what that is. And then this P right here is p-value. So in this case, standard error, this is my t statistic, and this is my p-value for two tails. Okay? So those are the necessary ingredients that we need for, let's say, to construct a confidence interval or conduct a hypothesis test. Now, we are not going to do inferences for intercepts, so do not even look at that first line. The only thing you need from that first line is whatever the estimate of the y-intercept is. But really, we're only going to be doing inferences for slopes. So this is the part that's highlighted in yellow is the part that you guys need to take note of, all right? All right, and then hopefully that's fine. And then the last slide before we get into the confidence interval is the sampling distribution of the sample slope. So provided that, you know, all the conditions are checked, you have data that's paired, or kind of, yeah, paired in that sense, where they come in XY pairs, all right? It follows that if you were to take all possible samples of the same size from the population, that the sampling distribution of the slope of that sample regression model is going to be approximately normal. So B is my estimate for the slope, approximately normal, where the mean is beta 1, which is the slope of that regression line in the population, with this variance right here. Notice that this is sigma squared, this is sigma x squared. This is not a typo. One does have an x, this one doesn't. So be careful with that, because again, if they were the same, obviously they would just cancel out, but they're there, you know, for a reason. And then because typically we do not know what the standard deviation is in the population, we're going to approximate this with the t-distribution with n minus 2 degrees of freedom. And provided that we could standardize and get a t statistic by subtracting the estimate and the hypothesized value, which is the null value, and then, or the center, and then dividing by the standard deviation, which is just the square root of that guy. Okay, so again, that's following the same sampling distribution mechanics that we had before. The only difference is that there's nothing in this slide that says central limit theorem, because the slope is not a mean or a sum. So central limit theorem does not apply in this situation, but it can be proven that the sample estimate is normal. It's just that I just didn't include it in the slideshow because it wasn't important to include at the time. All right. So now that we have the sampling distribution, now we could talk about constructing a confidence interval. But as of right now, do you guys have any questions about regression or any of the slides that I just covered? Yes, Miles?
Can you explain the conditional linearity slide?
Which one? Linearity?
Yeah.
So, explain what this condition is.
Yeah, kind of like this.
So, if we're going to be doing an inference for the slope, to my knowledge, there's only one type of function that has slopes. That's linear. So we have to make sure that there is a linear association between the variables in order for us to even consider a model that has a slope. So in this case, we have a condition called linearity because if we don't have anything, a relationship between two variables that's linear, then we shouldn't even be doing linear regression in the first place. So we check to see if there is a linear pattern so that we can proceed with doing an inference for that slope. Residual plots, yes. Okay. All right, and just to remind you guys as well, how do we look at residual plots to see if a linear model is appropriate? We want to see random scatter around this line. Like right here, it doesn't look like there's any apparent pattern in the residuals. However, in this one, which clearly is not linear, we see that there's an obvious curve in the residuals right there. So we want to see random scatter around the center line. That tells us that linear regression is appropriate for the data set. Okay? So residual plots are actually very important in diagnosing procedures like this. Okay? All right. Any other questions before I move on to confidence intervals? Okay. So confidence intervals, again, just to remind you guys, confidence intervals, we're using the point estimate to estimate what that value in the population might look like. So that's the same picture that I've used in the previous slideshow, where we use our point estimate as the center of our confidence interval. And from that point estimate, provided that it's an unbiased estimator, we extend that margin of error, and we hope with some degree of confidence that this interval around my point estimate will capture the true value. And then the idea here is that if we're doing a confidence interval for the slope, well, if this line in the middle is my sample regression model with a certain slope, well, if I'm doing a confidence interval for the slope, well, if the sample estimate is this slope right here, well, we're going to do a confidence interval, that gives us possible values of the slope for this model. So that's why this model could teeter in left or right, or more steeper or less steeper, because we're doing a confidence interval for the value of the slope. So obviously the slope can vary in value based on our confidence interval, because again, confidence intervals gives us plausible values for the slope. So obviously it will teeter around that center slope. Okay. All right. Again, confidence intervals don't need as much motivation as hypothesis tests, as we all know. So the confidence interval for the slope follows the same structure as before. It starts off with a point estimate, which in this case is B, plus and minus a critical value. Because we're dealing with a T critical value, it has n minus 2 degrees of freedom, which approximates the sampling distribution. And then the level of confidence is 1 minus alpha divided by 2. And at the very end is the standard error B, which the standard error B, I never seen any question on the AP test where you have to manually calculate the standard error. Typically you have computer output that will give you the standard error. And I don't even think your calculators give you the standard error directly. So again, I don't think it's something to stress. So I just left it as a standard error B right there, okay? And just to remind you guys, because we're dealing with the t distribution, to get that t critical value, you have to use the table or the calculator to get that value, all right? So just be aware of that, you know, the critical value is the same rules that we're playing with since when we started using the t distribution, all right? And then prediction intervals, I would have got to that if we had more time, but we don't. So here is the recipe for confidence intervals for the slope. So notice you have to state the parameter, which is beta 1, or you could just use beta because we're not talking about beta naught. So the college board will know if you put beta what you're talking about. We're doing a t interval for the slope. That's our procedure. The conditions, notice the conditions, there's a lot of them. Now, typically on the AP test, and I'm not going to say that this is always true, but this is generally true. So in general, okay, on the AP test, they're going to say that we're going to assume that conditions have been met. Have been met, okay? That's a general case. I'm not saying that you're never going to check conditions on the AP test because it's still a possibility that you may need to, but in general, you might get questions that say, oh, assuming conditions have been met, construct a confidence interval. In which case, that's step 2 you don't have to do because they're already giving it to you free of charge, okay? So just be aware of that, but there are 5 conditions for this stuff, and those are the conditions that I talked about in the slides at the beginning. But we also see, repeat offenders right here, which is independence and random sample, which have not changed since we started doing all of this stuff. But linearity, normality, and equal variance, those are the slides I covered at the beginning, because those ones are a little bit different, or either we haven't seen it before, or like normality, we've seen it before, but they kind of take a different form in these type of problems. The formula for a confidence interval is right here. Okay, that's the same as the slide before, and then the interpretation is the same as it was before. All right, so again, confidence intervals not as high maintenance as the hypothesis tests, equivalence. Okay. Any questions about confidence intervals before I jump into an example? 30 minutes. All right. In that case, if there's no questions, then we'll move on to the example. Right now, I would suggest that you guys put in the data because we're going to use the calculator functions for this. And you do have to put this in lists. So list 1, list 2, just like we did in unit 2. So do not put it in a matrix. It's not a two-way table in this case. All right, because this is one variable and this is another variable. So as you guys are putting that into your calculator, our objective is to construct a 95% confidence interval for the slope of the regression model that takes in the annual operation costs and the net revenue in millions of dollars. We have the data from Starbucks between the years of 1999 to 2007. So the data is there. Go ahead and input that in your calculators right now, because to use the function on the calculator, you do need the data, okay? All right. right. All right. So as you get, I still hear clicking. So once you have that in the calculator, I'm going to review how to find, let's say, the residual plot and so on and so forth, so that you guys know where to find that stuff and how to do it. So it is partly review for Unit 2 as well, but we will be using the calculator function to find the confidence interval for the slope. Based on first block, we may not get to hypothesis test today, which means I might have to finish tomorrow, so just be aware of that. For first block, I did not assign the next homework assignments, so for tonight, you guys probably won't get it as well. So just be aware of how our plans have changed a little bit, okay? So now that you guys have the data in the calculator, should be there, okay? List 1, list 2 for me. Let's look at the conditions first. So if you go to stat plot, which is right here in the top left corner, press second y equals. We're gonna go to our first stat plot, and I'm gonna select the scatter plot option, and I'm just gonna plot the x and y, just list 1, list 2. I just wanna see if the data has a linear relationship. That's all I want to do at the beginning right now. All right, so we have that. Hopefully you guys are still with me. We're gonna press graph and zoom 9 if you need to, and we're gonna see that, yeah, that data set looks pretty linear. It looks strongly linear. So I feel confident that, yeah, we could probably do these procedures. Yes?
Can you like redo that step? Like what you just did?
This part?
Oh, yeah.
Okay, so all I'm doing is selecting the scatter plot option, and my x list, y list is just the data set that I plugged in. So my x comma y, I'm just plotting it. And by doing so, once you click graph, you see the scatter plot, you'll see that it looks very strongly linear. Okay.
Wait, for me, instead of wireless, it says frequency.
Frequency? I would just put a 1 there if it's asking you for it.
Oh.
Yeah, I don't know why it's asking for frequency. Okay, unless you have a different type of the graph that you
Oh, wait,
selected.
never mind, yeah.
Okay. Alright, so hopefully you guys get something that looks like that. Clearly it looks linear. Alright, so I think the linearity condition is fine. Now, when you guys did the oh wait, we did not do the linear regression t-interval yet. Okay, so the next part is to look at the residuals. So in order for us to get the residuals, we're gonna go to our tests, and we're gonna go near the bottom, though I guess for me it's the second to last function, the linear regression t-interval. And you guys may have remembered from Unit 2 we did linear regression t-test before, but we're gonna do the t-interval right now. It's going to ask you for your list of data, L1, L2. Frequency, just keep as 1. Level of confidence, 95. And then the regression equation, you don't have to put anything for that if you don't want to. For right now, I wouldn't worry about it. And then once you get to there, press calculate. And then you're going to see, bless you, that the confidence interval for the slope based on the data that we have is right here. So there's that. And then I'm just writing it down right now. We have our estimate for the slope right here, which is the 0.4135 we see there. Degrees of freedom is 7 because we have 9 entries in our list. So 9 minus 2 because we subtract 2 for degrees of freedom, that's 7. We have S, which is the standard deviation of the residuals. And then we have A, the estimate for the intercept, and we have R squared and R. Okay. Notice that R is 0.999, which signals a very strong, almost perfect linear relationship. Okay. So now that we did the linear regression t-interval, now we have the residuals in our calculator. Just to remind you guys where to find the residuals, you're gonna have to go to your lists. So you see right here above stat, in blue is list. So press second stat, and then it has all the lists that you have. You're gonna go to the bottom and you'll see a list that's called resid. That's where the calculator stores the residuals for your regression. So you have to do the linear regression command before the calculator to know to calculate residuals, okay? Now, to do the residual plot, now that I know where my residuals are, I'm gonna go back to stat plot, second y equals, go here, and then I'm gonna still do the scatter plot option. I'm just gonna change my y list to that list of residuals. So if we go back to that list, press enter, you're gonna put the list of residuals in for y, and then the x, the y, or L1 you could leave the same, but all I'm doing is another scatter plot with the residuals. You press graph. Is everyone still with me? Press graph. You're gonna see nothing because you have to zoom in on it, so press zoom 9, and then there's your residual plot. Again, it doesn't look very impressive because we only have 9 data points. 9 is by no means very big, all right? So just be aware it doesn't look super impressive, and the reason for that is just because of a small sample size, all right? If I wanted to do a histogram of the residuals, you could go back to stat plot, and instead of selecting the scatter plot option, you could select the histogram option. And then the data that I want to do a histogram of is the residuals, or are the residuals. So in this case, I had to put my list of residuals inside of there, do the histogram. And then when you do that, you press graph, oops, quit. You have to zoom in on it. And then you'll see that there's the histogram of the data, or of the residuals, sorry, not of the data. Okay? So in that case, that's what that looks like. If you wanted to do a box plot of the data, you could select the box plot option right here, where again, you're still doing the residuals, and you see that the box plot is right there. You could zoom in on it right there, and that's my box plot. Okay. Notice that the box plot doesn't indicate any outliers. It is again it is skewed slightly, but when we use T procedures, as long as it's not extremely skewed, the T procedures will still be fine. All right. So that's our normality assumption, and then the equal variance is a little bit trickier because obviously we have a very small data set, so that we should expect a lot of variation there. All right. Anything else? Independence and random sample we'll have to go into as I write it up. All right. Any questions about how to operate the calculator as of right now? Yes.
Yeah, I'm still not getting the residual.
Did you do the residual t-test? Or not the linear regression t-test or t-interval first?
No.
You have to do that because how would the calculator know to compute residuals if you don't ask it to do a regression? Okay? All right, any other questions?
Well, you said T interval, right? Not T-test.
It doesn't, well, we're doing an interval right now, but if you just want the residuals, either one of them will do, all right? But right now we're doing a T interval, so it's probably better if you just do T interval, all right? Any other questions before moving on? All right, so the write-up. Okay, so the write-up is a little bit trickier, okay? For first block, I didn't give them the computer output, but because you guys are third block, I was able to do it. So the computer output for this problem looks like this, all right? So the computer output, notice that my explanatory variable, revenue, this is my X right here. And the estimate, this is the slope. The estimate for the intercept is A. The standard error right here, this is SE. So this is my standard error of my slope, which is what I need for my confidence interval. The t-value and the or the p-value, I do not need. These are for hypothesis tests, right? I don't need a t-statistic and I don't need a p-value for my confidence interval. Notice that it says degrees of freedom 7 right there. It also gives us the r-squared value as well as the standard error of the residuals, or the standard deviation of the residuals there as well. Okay, so computer output is very important for you guys to be able to read, all right? And just so you guys know, to find the standard error on your calculator, which is this guy right here, it doesn't give it to you. So that's why on the AP test it's more common for you guys to get computer output, because the computer output will give you the standard error where your calculator doesn't do that. So just be aware that you do need to know how to read the computer output for this. And then given all of this, now we have everything we need to write this up, all right? So step 1, and then let me insert my equation. Okay, so let beta be the true slope of the regression model of cost of sales on net revenue, both in millions of dollars. So notice that again, the parameter always has to be written in the context of the problem. So I'm saying that this beta is the slope of the model that has these two variables. So the variables that I'm talking about are revenue and cost of sales, which come from the table. All right, so just be aware that providing context at all parts is important. Okay, so to estimate beta, because I already defined it, okay, an appropriate procedure is a t-interval for the slope. That's all it is. All right, there's no hypotheses, so I don't have to do that. That's my first step. Okay? All right, so the second step, and again, I know that I mentioned before that it's common for the College Board to say, assume all conditions have been satisfied. I will write them out this time just so that you guys can see what it's like, but if they say that it's satisfied, then you don't have to do that, okay? So I will do it this time just so that you guys can see how it plays out. All right, so linearity is the first condition. That's going back to the recipe right there. So linearity, I already checked on a scatter plot. So a scatter plot of the data suggests a strong, or I could say a very strong positive linear association between the variables. So if there's a linear relationship, then I think linearity is good to go. All right. The second one is independence. This one is a little bit trickier because someone in first block, because this is talking about Starbucks, and it's talking about Starbucks between the years of 1999 to 2007. Someone in first block said that the how many years has Starbucks been in operation? I think they said it was about like 55, 57 years. And if we have 9, well, 9 times 10 is 90. They haven't been in operation for 90 years. So the independence condition, you know, is a red flag for us. But again, we're going to say that we checked it and proceed with caution going forward. So although sampling without replacement was done, and that the sample, or the population of years that Starbucks has been in operation is lower than 10 times n, which is 90 years, independence cannot be strict or cannot be technically achieved, but we proceed with caution. Okay, so again, I checked the conditions. It did not check out how I had hoped, so therefore we proceed with caution going forward. Okay, everyone see that? Okay, because we only have 9 years, and obviously if they've only been in operation for 50 something years, then we have a sample that's bigger than 10%. So obviously we checked it, but obviously it didn't go our way, but we are gonna move forward. All right. The next one is normality. Okay. Normality. Again, we only have 9 years. Doesn't work out, but a box plot of the residuals show no extreme outliers and no extreme skew. So under the robustness of the T procedures, okay, a T distribution with 7 degrees of freedom, and here, n minus 2, which is equal to 7 degrees of freedom, is a good approximation for the sampling distribution of sample slopes. Okay? So that's our normality. I checked the residual plot. Again, because we don't have extreme skew, no extreme outliers, I think that the normality assumption can be cleared because of the T distribution and its robustness to those strict normality assumptions. Okay? Next one is equal variance. Okay, sorry, I'm going to scroll up. Equal variance. A residual plot of the data does not indicate equal variance or equal standard deviation across all values of x, but that may be due to the small sample size. So we proceed with caution. Okay, so again, we want in the residual plot that the data points are spread around that line and is somewhat equal all the way across, but because we only have 9 data points, that residual plot didn't really look equally variable. So again, I'm just saying that I did it, but I'll proceed with caution because it wasn't cleared nicely. All right. So in that case, I checked it. The last one is SRS, or random sample. In this case, random sample, it didn't say it's not randomly selected because they're just taking a chunk of years. So we're going to just have to say that we're going to assume that this chunk of years is representative. So in this case, assume that the operating years of 1999 to 2007 at Starbucks are representative of all years, or of all operating years. Okay, so that's the best we can do. There's not random. It's not like they chose random years, right? They said we're just going to take the years from 1999 to 2007. They took a chunk of years. We're just going to have to say that we're going to assume that those are random, or not randomly selected, that they are representative. All right. So the conditions, obviously not pretty, but they are checked. Okay. And then now we're going to move on to the third thing. Oops, not that. Okay, which is the calculation. So calculations, B plus and minus the T statistic with 7 degrees of freedom and 95% confidence, and the standard error of B. This right here, if I plug in the values from my calculator, B was what, 0.41 something. I forgot what it was on the top of my head. The T statistic, or the critical value, if I do that one more time, with 7 degrees of freedom. All right. In this case, it's 2.3646, and then the standard error of B. This is coming from the output that's highlighted in pink up there. That's going to be 0.006677. So I'm just going to color code it so you guys know where I found that. All right. The calculator will not give you the standard error, unfortunately, and I had to remember what I told last year's students how to find it, but I couldn't think of it on the top of my head. So I'll get back to you guys tomorrow on how to find that. But that's the reason why College Board typically gives you guys computer outputs, because it does give it to you, whereas your calculator won't. Okay, and when you plug in these values in a calculator and you get it, that's going to give us that 397733, comma 0.42931 right there. That comes from the calculator, and then we're going to use that to interpret the value right now. All right. Okay, so step 4, in repeated sampling of size 9 from operating years at Starbucks. Okay, we say with 95% confidence that the interval from 0.39773. This should be dollars and millions, right? Or this should be dollars because we're talking about operating costs, and this, okay, both in millions, okay, captures the true slope of the regression model of operating costs on revenue. Okay, so that's the interpretation that we have used. Another interpretation that I've seen before, which I guess might be a little bit more correct or more what College Board's looking for, but I feel like this how you phrase it right here, that's in the spirit of confidence intervals anyways. But I have seen an interpretation like this, so you could write either one. Doesn't matter to me. 9 from Starbucks. Okay. We say with 95%, or let's say this, in repeated sampling, for every $1 million increase in X, which is revenue, okay, the increase in operating costs is captured in the interval 0, again, same thing right here, 39773 and 0.42931 in millions dollars with 95% confidence. Okay, so basically you're just saying that the slope is for every change in X by 1 unit, Y changes by this much. So you're saying that for every 1 unit increase in X, which is $1 million increase in revenue, we're going to say that that change in Y, the value of B, that whatever change that is going to be captured in our confidence interval. Okay, so remember that the slope is B over 1. This is the change in X. That's the change in Y. So we're basically saying that the confidence interval is for this guy right here, right? So that's what we're saying, that the change in Y, which is the value of the slope, is captured inside this interval for every change in X by 1 unit. All right, so I have seen it interpreted in that way as well. That one is more in context because you're actually interpreting the slope, whereas obviously the one that I typically like to do is just saying that the interval captures the true population parameter. Okay, so I don't think one method or one interpretation is more correct than the other, but you guys could use whichever one you prefer. All right. Okay. So that's the problem. All right. It's right there. Any questions on confidence intervals? Again, it's not a difficult confidence interval. It's just a little bit more work because it has more conditions and you have to get the information from different places, not just from the problem itself. Yeah.
Since it's a